We usually think of AI image generators as like basically just digital artists.
Right, yeah. You type in a prompt and it paints you a pretty picture.
Exactly. We look at the output, right? This highly complex photorealistic image, and we just kind of assume the AI is uh, incredible at mimicking patterns.
Yeah, we don't usually assume it actually understands the physical reality of what it just drew.
Right. We just assume it's really good at, coloring in the lines.
What's the difference between drawing a bicycle because you've, like, memorized the shapes
Uh-huh.
and drawing a bicycle because you intuitively understand how the gears, the chain, and the pedals physically work together to create motion?
Yeah, that makes total sense.
And for a long time, the consensus in the computer vision field was that generative models were purely those surface-level imitators. They were doing the former.
But what if the very act of learning to draw the world means you inadvertently learn to understand the physics, the logic, and like the actual depth of the world?
It's a huge question.
Welcome to today's deep dive. We are looking at a massive paradigm shift today. Google DeepMind recently dropped a paper dated April 23, 2026, titled Image Generators Are Generalist Vision Learners.
It's quite a title.
It really is. And the research essentially argues that these tools we thought were just digital artists are actually hiding like a profound comprehension of our physical reality. So, okay, let's unpack this, because our mission today is to completely rewire how you think about computer vision.
To appreciate the scale of this paradigm shift, we really have to look at how computer vision traditionally works.
Yeah, set the stage for us.
So if you wanted an AI to understand an image, say to recognize objects for a self-driving car, or figure out the exact distance to a wall, you use discriminative models.
Right, not generative models.
Exactly. You trained a highly specialized system to do one specific task using massive data sets of human-labeled examples. Generative models, the ones making the artwork, were totally sidelined for those engineering tasks.
Because the assumption was that they were too busy being artists to be engineers, basically.
Pretty much, yeah.
So to really get why this breakthrough is happening right now, I think we can map it onto something you, the listener, are probably already familiar with, which is large language models, or LLMs.
That's a really good parallel.
Right. Because a few years ago, researchers realized that if you train a model to simply predict the next word in a sentence across like billions of documents, something completely unexpected happens.
It doesn't just learn grammar or vocabulary.
Exactly. It develops emergent reasoning. It starts to understand logic, coding, context, all this stuff it wasn't explicitly programmed to do.
And DeepMind's core conjecture here takes that exact phenomenon and applies it directly to vision. They hypothesize that image generation training serves the exact same role as LLM pre-training.
So wait, predicting pixels is the same as predicting words?
Basically, yes. When an AI learns to generate images, specifically by denoising them step by step from pure static, it is practically forced to make sense of the world.
Oh, because it has to know what should be there.
Right. To correctly remove noise from an image of, say, a glass of water on a table, the model has to figure out how light refracts through curved glass.
Wow. Yeah.
It has to understand shadows, occlusion, object permanence. So predicting pixels essentially leads to emergent visual understanding.
I mean, it's like assuming someone who reads millions of books secretly understands human psychology, right?
Exactly.
We accept that with LLMs now.
Yeah.
But until now, we haven't assumed that someone who paints millions of photorealistic landscapes secretly understands the complex math of optics, lighting, and 3D geometry.
What's fascinating here is that there was previously very limited evidence that generative vision models had actually developed these robust capabilities.
Really? Nobody tried to test this before?
Well, some earlier attempts tried to use image generators for vision tasks, but they required adding these really clunky architectural modules, or they had to completely retrain the model.
Which kind of ruins the whole point, right?
Yeah, doing that usually destroyed the model's ability to actually generate images in the first place. But the researchers at DeepMind proved that these internal geometric representations were always there.
Just hidden beneath the surface, waiting to be tapped.
Exactly.
So if the knowledge of physics and geometry was locked inside this digital artist the whole time, how do you force it to pick up a brush and actually show you?
That's where the methodology comes in, and it's brilliant. They started with a foundational image generation model called Nano Banana Pro.
Gotta love the AI model names, Nano Banana Pro.
Yeah, very catchy. So then they performed what they call instruction tuning to create a new generalist model, which they naturally named Vision Banana.
Of course. So how does instruction tuning actually work here?
Instruction tuning is another concept borrowed straight from the language model playbook. You take a base model that just generates raw output and you give it a small amount of highly specific data.
Just to teach it how to, like, follow instructions and format its answers properly.
Exactly. DeepMind mixed a tiny, really lightweight amount of computer vision task data into Nano Banana Pro's diet, so to speak.
And instead of forcing the model to output complex mathematical data or coordinate grids, they did something kind of wild. They seamlessly reframed the very concept of perception.
They
They
did.
just asked the model to communicate its perception by generating an image. They parameterized the vision task outputs as RGB colors. It's what I like to call the RGB trick.
The RGB trick, yeah, it's so clever. If you want the model to identify a skateboard in a photograph, you don't ask it for a mathematical bounding box.
Right, because it's an artist.
Exactly. You just prompt the model, segment the skateboard category in pure yellow.
That's insane.
You literally give it the exact RGB color code, like angle brackets 255, comma 255, comma 0.
And then what happens?
The model processes the image and simply draws a perfect yellow silhouette over the skateboard. And then researchers can decode that color back into a traditional computer vision mask simply by grouping the yellow pixels together.
Okay, I have to admit, when I first read this part of the paper, I was deeply, deeply skeptical.
Oh, really? Why?
Well, wait, so we're just asking a digital artist to paint by numbers. I mean, is it really that simple to hack a generative model into a highly technical computer vision tool?
I get that reaction.
It sounds almost too simple to actually work in a rigorous engineering environment. Yeah.
It sounds incredibly simple, but it's not a hack. It is a unified interface.
Okay, explain that.
Think about how text generation acts as the universal interface for language tasks. Whether you are asking an LLM to write a poem, debug a Python script, or translate French, the interface is always just text.
Oh, wow. Yeah.
DeepMind is proving that drawing RGB images acts as the universal interface for visual understanding. By doing this, they essentially calibrate the model's abstract internal knowledge into measurable physical geometry and semantic labels.
Okay, so with this unified interface in place, I guess the real test is seeing how well it performs when it goes head-to-head against specialized tools.
Right, the model's built from the ground up to do absolutely nothing but segment images.
The ones backed by massive budgets and highly curated data sets.
Exactly. And the 2D scene understanding benchmarks are the perfect place to start. This tests the model's ability to ground natural language and highlight corresponding objects in a scene.
So they tested Vision Banana on semantic segmentation, instant segmentation, and referring expression segmentation.
And how did it do?
The results blew me away. I mean, on the Cityscapes benchmark, which is a classic test where AI has to categorize pixels into 19 classes like road, person, truck, or sky.
Yeah, a very standard test.
Vision Banana completely beat a highly specialized model called SAM3. The paper mentions it scored an MIU of 0.699 versus SAM3's 0.652.
That's a huge jump.
It is. And just to translate that for a second, MIOU basically measures how perfectly the AI's coloring stays inside the lines of the actual object.
All right.
A score of nearly 0.70 doesn't sound like a perfect 100%, obviously. But in the messy, chaotic real world of computer vision, it is incredibly high. And it also matched DanoX on instant segmentation.
The reason this is so significant comes down to how these models actually learn.
Yeah, how so?
Well, specialized models like SAM3 rely heavily on massive volumes of expensive human-annotated mask data. Humans literally sit there and draw outlines around objects to train the AI.
Which sounds tedious and prone to error.
It is. That means the AI is limited by human error and rigid predefined categories. But Vision Banana doesn't rely on human outline.
It uses pre-trained generative priors, right?
Exactly. It learned where objects naturally separate in the real world by having to reconstruct billions of noisy images from scratch.
That deep foundational learning really shows up in the referring expression segmentation part of the paper. Because it's an image generator trained on text prompts, its ability to understand nuanced descriptive language is just staggering.
The examples in the paper are fantastic.
They are brilliant. I was looking through them, and you can literally tell it to segment a stretching cat in green and a cleaning cat in cyan.
And it gets it right.
Flawlessly. It highlights the cat reaching up against a shower door in green and the one licking its paw in cyan. It can segment distinct pieces of garlic on a plate of beef, coloring each individual clove a different color.
That's impressive detail.
It can even differentiate between crescent-shaped croissants and regular croissants in a bakery display.
That bakery example is so important because it highlights a profound compositional understanding of language applied to visual geometry.
Right, it's not just fine pastry.
Exactly. The model isn't just looking for the generic, flaky texture of a pastry. It understands the geometric modifier crescent-shaped and successfully applies it to the noun croissant.
And I also read that menu.
Yes.
Yes.
It successfully read a complex Chinese and English menu hanging on a wall just to locate and segment the chef's name, rendering just the text of the name in cyan.
Okay, but here's where it gets really interesting. My absolute favorite example in the entire paper involves a toaster.
Oh, the toaster example is a classic.
Right. There's a photo of someone at a convention, and they have a kitchen toaster hooked up to a laptop and a monitor. They are literally using the toaster's levers to play a video game.
People do the craziest things at those conventions.
Seriously. So the prompt asks the model to segment the game control device in solid yellow.
Now, a traditional computer vision model sees the metallic edges, the bread slots, the chrome finish, and categorizes it strictly as a kitchen appliance.
Because that's what it was trained to do.
Right. It fails the prompt entirely because it's locked into its rigid training categories.
But Vision Banana perfectly highlights the toaster in yellow. It understands the context. It sees the wires connecting it to the computer, the human hands resting on the levers, the gameplay on the screen in front of it.
It's evaluating the whole scene.
Yeah, it reasons that in this specific environment, the toaster is functioning as the game controller. That requires deep emergent reasoning. It's evaluating the relationships between objects, humans, and their environment, rather than just looking for standard, toaster edges.
This is the exact advantage of generative pre-training. The model has absorbed a massive, completely unfiltered distribution of world knowledge. But as impressive as that 2D pixel reasoning is, the true test of physical understanding is the transition from 2D logic to 3D geometry.
Oh, yeah. Because a photograph is entirely flat.
Yeah.
It only has an X and a Y axis.
Right.
To estimate depth or surface angles, the AI has to somehow infer the invisible Z-axis, the depth, from a single flat image.
Which is not easy.
Not at all.
Yeah.
It has to understand scale and distance without the benefit of stereoscopic vision or multiple camera lenses or laser sensors.
Monocular depth estimation is notoriously difficult. It is an inherently ill-posed problem because projecting a 3D world onto a 2D plane mathematically discards critical geometric information.
Right. The data is literally just gone.
Exactly. Most specialized, state-of-the-art models rely on knowing the camera's intrinsic parameters, like the focal length or the sensor size, to essentially cheat their way into estimating depth accurately.
But Vision Banana crushed the 3D tasks anyway. I mean, it beat depth, anything 3 on metric depth estimation, and it beat Lotus 2 on surface normal estimation.
The kicker is how it did it.
Yeah, it achieved this with 0 real-world depth data in its instruction tuning, and absolutely no camera intrinsics during inference. It did it entirely blind to the camera hardware.
How they managed to instruct a model to output highly precise metric depth using only RGB colors is honestly one of those elegant parts of the research.
Let's explain that, because it's tricky.
Well, you have depth, which could range from 0 to infinity meters, right? And you have to represent that using colors bounded between 0 and 255.
Wait, I'm trying to visualize this.
Yep.
They are mapping physical depth onto a 3D color cube. How does a color equal a physical distance, especially when distance is so relative depending on how far away you are looking?
That's the challenge. They couldn't just say, make 1 meter red and 2 meters green because our perception of depth isn't linear.
Right, obviously.
So they apply a mathematical curve. The paper calls it a power transform with the shape parameter lambda set to -3.
Okay, lambda -3. What does that actually mean in plain English?
What that actually means is they drastically exaggerate differences up close while compressing differences far away.
Oh, I see.
If you are reaching for a cup on a desk, a difference of 2 inches matters immensely. But if you are looking at a mountain range, a difference of 100 feet is practically invisible. The math prioritizes precision for near-field objects.
Oh, it makes total sense.
Yeah.
And once they curve that depth, they run along the edges of an RGB color cube. The paper compares it to a 3D Hilbert curve.
Yes.
Imagine like a continuous winding line starting at the black corner of a 3D color cube, snaking through the red, green, and blue edges all the way to the white corner. They map the exact depth values along that line.
It creates a perfectly reversible two-way street, which mathematicians call a strictly invertible bijection.
So the model generates a brilliantly colored false color image representing depth.
And the researchers can mathematically decode those exact colors back into precise metric distances without losing any data.
That is so cool.
And they did something very similar for surface normal estimation, which is figuring out exactly which way a physical surface is pointing in 3D space.
Like the angles of walls and stuff.
Exactly.
If a wall is facing to the left, the model colors it pinkish red. If the floor is facing up, it colors it light green. If an object is facing directly at the camera, it's light blue.
It's incredibly intuitive.
It is. You can just look at the generated image and instantly see the invisible 3D geometry of the room encoded in these vibrant colors.
The visual fidelity is remarkable, too. In the comparisons against Lotus 2, Vision Banana's surface normal maps capture incredibly fine granular details.
Like what kind of details?
You can see the exact curve of a wooden chair or the subtle angle of a ceiling molding. These are details that specialized models tend to smooth over or blur out.
Which brings us to a real-world test. Because, academic benchmarks like NYU V2 or Kitty are great for research papers, but the authors did a real-world vibe test that really drives this home.
Oh, the Kinkakuji example.
Yeah. One of the authors was visiting Kinkakuji, the Golden Pavilion in Kyoto, Japan. They took a casual, everyday photo with their smartphone. Just a standard picture of the pavilion sitting across a pond, framed by some pine trees.
It was a completely unseen environment taken with an unknown consumer camera sensor in variable outdoor lighting. A true test in the wild.
Right. They feed this single photo into Vision Banana. It generates the depth estimation image using that winding color curve we talked about. They decode the color at a specific spot on the far bank of the pond, and the model estimates the distance to be exactly 13.71 meters.
Which is incredibly specific.
It is. Then, the author goes onto Google Maps, finds the exact spot they were standing, measures the actual distance to that point on the bank. And the actual distance is 12.87 meters.
That is wild. From a single, flat smartphone photo, that is an error rate of just about 6%.
Yeah.
It was off by less than a meter on a target that was over 40 feet away.
This is huge for anyone who uses a smartphone. Think about how your phone currently takes a portrait mode photo with a blurry background.
Oh, yeah. It usually relies on LiDAR sensors or comparing slightly different images from multiple lenses to figure out what's in the foreground and what's in the background.
But this AI figured out the exact distance to the water in the building using a single flat image.
Just from context.
Right. It inferred the absolute scale of the entire scene just by understanding the relationship between the water, the trees, and the architecture. It fundamentally changes what we might need hardware to do in the future.
If we connect this to the bigger picture, it raises a critical question about the nature of this model. It has clearly become a genius at state-of-the-art computer vision tasks. It understands 2D context and 3D physics.
Yeah, it's doing it all.
But the ultimate test of a true generalist is whether it sacrificed its original purpose to achieve this. Did the instruction tuning ruin the art?
That's a great question.
Did it forget how to be an image generator to become a physicist?
Well, the researchers ran it through GenAI Bench for text-to-image generation and ImEdit for image editing. They benchmarked Vision Banana directly against its original base model, Nano Banana Pro.
And the results?
The answer is an emphatic no. Vision Banana maintained a 53.5% win rate on text-to-image and a 47.8% win rate on editing.
That's essentially a tie.
Exactly. It performed essentially on par with the original artist. It didn't forget how to generate gorgeous high-fidelity images. It just learned a new way to express its underlying physical knowledge of those images.
That retention of generative power proves that the instruction tuning was incredibly lightweight. It didn't overwrite the model's brain.
It just taught it a new language.
Precisely. The RGB color maps were just a new way to communicate what it already intuitively knew about the world.
So what does this all mean for you, the listener? Why should you care about a generalist model if domain-specific specialist models already exist and do a pretty decent job?
It really comes down to how generative models handle ambiguity. When a specialist discriminative model is unsure about the boundary of an object, or, say, the exact depth of a shadow in a complex scene, it tends to collapse to a blurry average.
Kind of like hedging its bets.
Exactly. It hedges its bets to minimize its statistical error. But generative models, by their very nature, are designed to map the full distribution of reality.
Oh, right.
When faced with uncertainty, they don't produce a blurry mean. They generate a highly detailed, physically plausible hypothesis based on their vast world knowledge. They don't hedge. They commit to a reality.
That makes a lot of sense. This isn't just an iterative improvement in software, then. This is a massive shift in how we approach artificial intelligence entirely.
It absolutely is.
Just as LLMs swallowed natural language processing and replaced thousands of specialized text tools, generative vision pre-training is poised to swallow computer vision.
The researchers actually suggest this paves the way for AGIV, which stands for Artificial General Intelligence from Vision.
Wow. AGIV.
We are moving toward a single, unified OMI model. Imagine one foundational system that can generate a movie scene from a text prompt, edit a photograph, guide a robotic arm precisely in 3D space to pick up a fragile object, and accurately segment medical imagery, all using the exact same underlying parameters.
That is just, it's mind-blowing. Let's do a quick recap of what we've covered today because it's a lot.
Yeah, let's summarize.
We started with a foundational image generator, Nano Banana Pro, a tool built just to paint pictures. By applying a lightweight instruction tuning phase with a brilliantly simple RGB color trick, DeepMind unlocked massive hidden capabilities.
Hidden the whole time.
Suddenly, this digital artist outperforms highly specialized tools in complex 2D reasoning, like figuring out a toaster is being used as a game controller. And it masters 3D geometry from flat images without needing any camera hardware data.
And it manages to do all of this while retaining its full artistic abilities.
It conclusively proves that the act of visual creation inherently requires a profound, internalized comprehension of the visual world's underlying structures.
To draw the world accurately is to understand the world physically.
Which leaves us with a final, lingering question to ponder. If an artificial intelligence learning to draw the visual world inadvertently masters the hidden 3D physics, logic, and depth of that world, what does that mean for human imagination?
It's a deep thought.
When you close your eyes and visualize a new invention or picture a complex scene from a novel you're reading, do you already possess the hidden physical blueprints for it in your mind's eye, just waiting to be decoded? Or are we all walking around with an intuitive physics engine running quietly beneath our daydreams?
It really makes you wonder.
Next time you imagine a space, remember that the act of picturing it might mean you already understand its geometry. Thank you for joining us on this deep dive. Keep questioning the world around you, and remember, sometimes a breakthrough tool you need isn't a specialized machine, but an artist with the right set of colors.